Okay, here's week 3 of Algebra. We have book assignment Monday and Tuesday, worksheet Wednesday, another book assignment Thursday, and quiz Friday. Again, if you have any questions, you can email me right there. All right, let's get started. Excuse me. We're on 10.2, that is on probability. All right, we're going to go right to an example. Let's say we're talking about marbles here. We have blue marbles, yellow marbles, red, and white. 6 blue, 8 yellow, 5 red, and 1 white. And we want to know what's the probability, which we will just use capital P from now on. So basically what this says is what's the probability of picking a Y. Now probability is number of successes over total number. And we're assuming everything in this chapter is done at random. If this was a bag of marbles and we can look in the bag, well, our probability would probably be 100% then. But we're going to say it's at random. So the first thing we want to do is find the total. Total number of marbles would be adding these 4 numbers together. 6 plus 8 plus 5 plus 1 is 20. So that's our denominator. The numerator would be how many of whatever it is we're looking for. In this case, yellow, which is 8. So there's our answer, 8 over 20. We could keep the answer like that, or we could reduce it down. Again, our calculator could help us reduce it down. We go 20 divided by 20 divided by 8 divided by 20. Let's try that again. 8 divided by 20. Then we hit math. It's already set up for fraction. Enter, enter. And that will reduce the fraction down. 2/5. We could also make it a decimal, which would have been 0.4, but usually it's better to keep it as a fraction. What's the probability of blue or red? When you see or, that means we're going to add. The bottom number, the total number, is still going to be 20. But now the top number is blue or red. Blue is 6, red is 5. We're going to add those together to get 11. So the answer is 11 over 20. Third question, what's the probability of picking a colored marble? All right, assuming these are all colors, then it would be 20 over 20, which is just 1. We could change these to percentages too. I'm not going to, but we could have said 100% for this first one. 0.4 becomes 40%. So these could have been expressed as percentages too, but I usually keep them as, it's probably best to keep them as fractions or whole numbers if they work out even. What's the probability of picking a green marble? Again, there are no green marbles, so this would be 0 out of 20 or 0. Next example, we're going to flip 3 coins. What's the probability of them all being heads? Now we could act this problem out. Flip the first coin, second coin, and third coin, and list all the probabilities, all the possibilities. So, and you want to try to have an order that you're doing this. So they all could be heads. The first 2 could be heads, and the third one could be tails. It could be heads, tails, heads, or heads, tails, tails. If you notice, I'm trying to keep a pattern here. So these are 4 possibilities where the first one is heads. Well, if there's 4 possibilities where the first one's heads, there must be 4 where there are tails. Basically, I could just copy the last 2 columns again. So we have tails, heads, heads, tails, heads, tails, 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 heads, and finally all tails. So again, the probability is success over total. There are 1, 2, 3, 4, 5, 6, 7, 8 possibilities. How many of them have all heads? Just one of them. Now, that's one way of doing it, but this can get pretty tedious if we say we flip 50 coins. So another way of doing it is, again, I make my 3 columns, first, second, and third, and I think what's the probability of each one of them? So if I flip 1 coin, the probability that it's heads is 1 out of 2. It's either going to be heads or tails. The second coin would also be 1 out of 2, and when I flip the third coin, the probability of that being heads is also 1 out of 2. And since these are 3 different events, what we do is we multiply them. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. So this is probably the way we want to do it most often. Let's do another example. Let's say these are scores, whatever, maybe on a quiz or on homework out of a 10-point scale. So all of these are single-digit numbers except for the 2 10s. There should be 10 scores. First question, what's the probability of getting a 9? And that would be exactly a 9. Like all the other ones, the first thing we'd want to do is figure out how many there are. Like we said, there are 10 scores here. There are 10. Now, I did not add up the numbers, but I added up how many scores there were, how many quizzes or how many homeworks there were. So there were 10 of those. Of those 10, how many of them got a 9? 1, 2. 2 out of 10. Again, we could use our calculator to simplify that down if we need to. 2 divided by 10. Math, enter, enter. 1/5. We could make it a decimal, we could make it a percent, and all that other stuff. Now I'm going to ask what's the probability of at least an 8. Again, the bottom number is going to be 10. Now how many are at least 8? What that means is 8 or more. 1, 2, 3, 4, 5, 6. 6 out of 10, which reduces down to 3/5. Last question. If there are 150 students, so again, let's just assume these were quiz scores. These were 10 students on their quiz scores. Let's say I have 150 students. Estimate the total number who scored at least an 8. So basically 3/5 of my class or whatever, or 60% had at least an 8. So we can make a proportion here. So I can take the answer from the previous problem and set up a proportion. Now, similar to chapter 2, this is your success, this is your total. The 150 represents a total, so it should go at the bottom, or it needs to go at the bottom. What we're looking for is a successful score of at least 8. That would go at the top. We cross multiply. 5 times x is 5x. 3 times 150 is 450, and then we just solve. We'll divide both sides by 5, and x equals 90. Check to see if the answer makes sense. We have 150 students. Estimate the total number that scored whatever, 8 or higher. That makes sense. It needs to be a number less than 90. Last thing, we have two definitions. We have experimental probability and theoretical probability. So these are both probabilities. The experimental probability, if you look at the root word experiment, that's what did happen. So we didn't experiment. So this is the probability of what did occur. Where theoretical probability is the probability of what should occur. So I'll give you an example. If I flip 10 coins, I should get 5 heads and 5 tails. So the theoretical probability of flipping 10 coins is 50% heads, 50% tails. Let's say I just did this experiment. And in my experiment, I got 7 heads and 3 tails. I didn't do anything wrong. That's just what the results were. The experimental probability would be 70% heads and 30% tails. Where again, the theoretical is what should have happened, 50% of each. Now, how do I get the experimental to be closer to the theoretical? Because right now they're pretty far apart. To get the experimental closer to the theoretical, we would do more trials. So if I did this experiment 1,000 times or 1,000,000 times or 1,000,000,000 times, especially on a computer, we're going to get 50%. To get experimental closer to the theoretical, do more trials. Okay, that's lesson 1. Lesson 2 will be 10.3. Random outcomes. This is similar to the first lesson, but just adds a little bit to it. The probability of something occurring, I'll just say that's a yes, plus the probability of it not occurring, which I'll say no, has to always equal 1. So the probability that it rains today plus the probability that it doesn't rain today has to equal 1. It either does or it doesn't happen. All right, let's do an example. Let's say I did an experiment where I released a bunch of bees into the air. 247 bees fly east. 628 bees fly west. What's the probability that they flew east? Again, like a lot of the other ones, the first thing we want to do is find the total. We add 247 plus 628, and that's going to equal 875. Okay, so that's the denominator. the top number is success, well, east would be 247. What's the probability of flying west? I could subtract this from 1, but I think it's just as good to do it the same way we did A. So again, the total is still 875. The top number is 628. Now the new thing, the third question is, what assumptions were being made here? So basically, what could cause this data to be skewed? And there's a lot of answers. Really, you could almost say anything and the answer would be true. What you don't want to say is that the data was wrong. All right, the data already happened, so we don't want to say the data was wrong, but what caused this data to happen? All right, so usually you could say anything that deals with the weather in a problem like this. Like if there's a storm to the east, obviously bees are not going to fly towards the bad weather. If we're talking about living things, some could have died, or opposite reproduce. All right, so a lot of different answers for that too. Maybe there's wind, which again I guess would be weather. Maybe there's flowers. There's more flowers to the west. So when you're doing an activity or an experiment, you want to try to control all these variables, or else the study or the activity is kind of pointless. All right, let's do another example. Let's say we have 20 applicants for a job. And there are 5 openings. First question, what's the probability of getting hired? Again, the total would be 20. The success would be 5. We could reduce that down to 1/4 or 25%. Like the previous problem, let's ask this question again. What assumptions were being made? Now, I think we all know that if 20 people are applying, they all don't have the same chance of getting the job. So some are more qualified. There could be good reasons or bad reasons for it. Whatever, good interview. So these would be good reasons. Bad reasons could be maybe the relative is on the hiring committee. If your mother or whoever is on the interview committee, you probably have a better job of getting that than someone else. All right. So there's a lot of different things, good or bad, why people don't have the same chance to get the job. On the quiz or test, you only have to give one reason. We don't have to give 4 or 5 reasons, but one reason. Oops. All right, let's do one more example. We flip a plastic cup. So we flip it up in the air, and it can land in one of 3 spots. It could land on its base, the top, or the side. So just take a can of soda or something like that. You can just picture a can of soda. Lands on the top, the bottom, or the side. What's the probability that it lands on its side? Now, without the assumptions, we have 3 answers, and only one of them is the side. But I think we understand that that's not true. If we're going to flip it on in the air, there's a very good chance it's going to land on its side, like almost pretty much almost 100%. And the reason for that has to do with surface area. That's probably the biggest one. I'm sure we could think of others. How high you throw it, how high the toss is. So if I just throw it just a little bit, the chances of landing on its base are a lot better, or the top. But all right. So that's the second lesson. Third lesson, 10.4, is on permutations. What a permutation is a group arranged in a certain order. And the key word here is order. So order is important. All right. So when they give you a little story problem, like the one I'm about to give you, you want to first figure out, does order matter? All right, so the first problem here, a group of 2 people found 7 seats. Find the number of ways to sit. Now, another way of saying that is, how many different ways can they sit in those 7 seats? So sitting in seat number 1 is different than sitting in seat number 7. Sitting 3 spots from your friend is different than sitting right next to your friend. So order is important. Right, it's kind of like a seating chart. Okay, so this is a permutation. The formula for permutation is this. Now I need to explain what this stuff means, but what we have here is the probability of n choose r, where n represents the number available, and r represents the number used. That's equal to n factorial. What a factorial is, let's write that over here. What a factorial is the product of natural numbers decreasing down to 1. So for example, 5 factorial would be equal to 5 times 4 times 3 times 2 times 1, which is 120. All right, so anyways, the formula is n factorial over n minus r factorial. So the number available would be 7. All right, so let's do this problem down here. So really the left side, which is not as important, but I'll write it anyways, the bigger number always will go first. 7 choose 2. That's how we read that. So the 7 goes at the top, 7 factorial, and at the bottom it'll be 7 minus 2 factorial. Let me first show you how you can do this without a calculator. We do the subtraction. 7 minus 2 is 5 factorial. Now what 7 factorial means is 7 times 6 times 5 times 4 times 3 times 2 times 1, and 5 factorial is 5 times 4 times 3 times 2 times 1. Look where I put the 5. I lined it all up. These cancel out because this is just one big multiplication problem. This is not a binomial or anything bigger. So the only thing that's left is 7 times 6, which is 42. Now, we normally are not going to do that, but I did want to show you how you get that answer without a calculator. All right. How you get it on the calculator, let's see if I can remember. Oh, probability. Okay, there it is. All right, so we go math, and then we get the probability. The quickest way is actually to go left arrow. So let me just start over again. So we go math, here's probability. So I could go right 3 times or I could go left once. We're doing permutations today, so we're going to hit 2. Tomorrow we're doing combinations, or not tomorrow, but the next lesson is combinations, so that would be 3. But for this one, we're doing 2. All right. Now I forgot to put the first number down before I hit this. So I have to restart again. You put the n value first. So in this case, it's a 7. Then I hit math, left arrow, 2, and then I hit the second number, call that the R value, which in this problem is the 2, and then we hit enter, and there's our 42. All right, so let's do another example, and I'm going to use the calculator from now on. The probability of the permutation of 5 choose 3. So that actually led me to my question, how do you know if the capital P stands for permutation or probability? If there are 2 numbers in a parentheses with a comma between them, it stands for permutation. Whereas if it's just the probability of heads, all right, like probability of a 9 or the probability of heads, then the capital P stands for probability. But if you have 2 numbers separated by a comma, then it stands for permutations. All right, so the permutation of 5 choose 3. So again, we punch in the first number, 5. Then we go math, left arrow. Again, it's permutation, so it's 2. And then the second number is 3. We hit enter, and we get 60. Don't even have to show work. Try another example. We have 4 kids, 4 seats. Number of ways to sit. So anytime you see a sitting problem, very good chance it's going to be order matters, permutation. Where tomorrow, order won't matter, or I should say the next lesson. So basically we have the permutation of 4 choose 4. 4, math, left arrow, 2, and then the second number is 4 again. That gives me 24. Now another way of knowing that or getting that is, this you don't need to know, but I think it's good to know. If the n and r are the same, then the answer is just going to be n factorial. So in this problem, 4 kids, 4 seats, really the answer is 4 factorial, which is 24. The last thing that we need to know, it's not that important, but it's good to know. If we have 0 factorial, that's equal to 1. We have a worksheet that goes along with this. Here's the worksheet. Might have to freeze the video to get that down. Okay. Thursday's lesson. This is technically the same section, so I'll call it 10.4b, and now we're looking at combinations. Permutations is where order matters. Combinations are where order is not important. Arrangement, where order not important. So so for example, your locker combination is actually not a combination at all. It's a permutation. You have to go to the first number, then you go to the second number, and then third number. All right, so whoever came up with the definition of locker combination doesn't even know what a combination is. So a combination is where order is not important. That would be like if I said, hey, can I have 5 volunteers to come to the board? We're picking teams for playing basketball. Who I picked first, second, third, fourth, or fifth doesn't matter. All right, so for example, say I'm the basketball coach and I need to pick 5 starters from a team of 7. It doesn't matter who I pick first, second, third, fourth, or fifth. I just need 5 starters. Now, if I assign a role to each of them, like you're the point guard, you're the shooting guard, you're the post, whatever, then it becomes a permutation. But if I just say 5 starters, hey, go out there, then that's a combination. Order is not important. So we call that C for combination. Now my C looks like a parentheses. 7, choose 5. The formula, I guess I should have wrote that down. Let's see, I'll just write it up here. The formula is very similar to permutation, where it's n factorial at the top and n minus r factorial at the bottom. But the only difference is there's another r factorial at the bottom. So we're actually dividing by a bigger number, which means the answer will be smaller. Now we can just use the calculator for these, so we don't even really need that formula. So it's done very similar. So we punch in the first number, 7. Math, we go to probability. But now instead of hitting 2, I need to hit 3. All right, so 3 is combination. Hit the second number, 5, and there's the answer, 21. Let me just show the work